Good morning everyone. Welcome to the fourth video on relativistic effects, namely time dilation, length contraction, and simultaneity. So until yesterday, the previous video, we had just been looking at what are these phenomena, and I felt we need to solve some problems based on this. So let us start solving some problems, and then we will go on to the next part. Okay, so towards it, let me just give a recap of what we have learned so far. So in the first video, we had learned about Galilean transformation. We learned about what is Galilean transformation, as you can see there, that you can convert if there are two frames. One is a stationary frame, another one is a moving frame, and the moving frame moves with the relative velocity v. Then with respect to stationary frame, then you can see the coordinates in the moving frame or in the stationary frame can be related to moving frame as x equal to x dash plus vt, y equal to y dash, z equal to z dash, and so on. And in a similar way, you can also relate the velocities. Okay, so what is the velocity as measured in the primed frame, that is the moving frame, with respect to the stationary frame, and so on. So this is what we have learned in your Galilean transformation. But this Galilean transformation will fail when the speed of the object is much larger. So as a result of it, we derived or we got one more set of transformation equations known as the Lorentz transformation equation. What does this tell you? This tells you again the position and the time coordinates. The difference between the Galilean transformation and the Lorentz transformation is that in Galilean transformation, only the space coordinate is varying. But here, the time coordinate is also varying. That's what we have seen. And then the values of it was given. And then we define something called as the Lorentz factor given by gamma, which is equal to 1 by square root of 1 by root of 1 minus v square by c square. We have seen this also. Next, after this, we looked at what you mean by length contraction, time dilation, and so on, and simultaneity also in the previous video, in the third video. Now, in this fourth video, we are just looking at what are the problems that you can anticipate in this. Okay, how to solve these problems. Okay, because many students had said that okay, the problems were not adequate in the what you call these in those videos. Personally, they had messaged me, so I thought, okay, why not we introduce something like problems in this, especially on understanding the proper length and proper time. Okay, so towards it, let us start with this. So as you see, I have shared my screen here. You can see the first problem is about length contraction. So I'll read the problem. An object of length L0 is inclined at an angle theta moving with a speed v. Okay, so it is something like this. You have an object of L0. So this is your L0, a pen, for example, a rod, okay, whose length is L0. And this is moving with the speed v. Now, which is a proper length? Proper length is L0. And where am I measuring? I am now the observer sitting in the moving frame. What will be the length of this rod in the stationary frame and what will be the new angle? Okay, so now if I view the same pen from a stationary rod, then what will be the length of this rod? What will be the length of the rod? Definitely length contraction will be there, and as a result of it, length would be seen smaller. First thing. And what will be the new angle? Will the angle, if this is making an angle of something like 60 degree, is it making the same 60 degree or is it lesser than that? That's what we need to know. Okay, so now let us solve this problem. Let me share my screen with you and then we will solve it. Okay, now I shared my screen. I hope you can see this. Okay, now as you see, this is the rod, this is the angle theta, and this is your length L naught. So what I will do is I will split this L naught, length L naught, into two parts. Along this direction, let me change my pen, but it's visible to everyone. So this is your L0 cos theta. I taken the component of L0 along the x-axis, and along this direction, it should be L0 sin theta. But you are watching this pen, you are watching the length of this pen from an observer from a stationary frame. Okay, now what we do is we need to find out, so what happens with this length along the x-axis. Now along the x-axis, let us say this is your Lx. Lx will now be equal to L0 cos theta into square root of 1 minus v square by c square. What is this? This is nothing but you found out what is the length of the frame, that is the length contraction has happened. Okay, within the stationary frame, this is what is the length along the x-axis. Along the y-axis, what will happen? Along the y-axis, the rod is not moving along the y-axis. It is moving only along the x-axis with a speed v. So there is no change. So I can now write Ly is equal to L naught sin theta. There is no gamma factor coming into. Okay. Now once when we have all this, now what is the next thing? Now this Lx and Ly will look like this over here. This would be your Ly and this would be your Lx. What is the length over here? Length L will be equal to, by Pythagoras theorem, Lx square plus Ly square. Now let us substitute this. I will do one thing. I'll write it over here. I can now write L is equal to square root of, for Lx square, I can write this as a L naught square cos square theta, L naught square cos square theta into the square and root goes away. So it becomes 1 minus v square by c square plus this Ly square should be L naught square sin square theta. Sin square theta. We have got all of them now. What's the next thing? Now next what I can do is, see, L naught square is common here. So I'll take out common L naught square inside the brackets over here. L naught square into, so here I have cos square theta minus v square by c square cos square theta plus L naught square is common, so sin square theta. Now you see this cos square theta plus sin square theta, what is it? It's equal to 1. So I can also write this as equal to square root of L naught square into 1 minus, see, I have combined these two, minus what is the remaining? Minus v square by c square. V square by c square cos square theta. This is what is remaining. I can keep it like this. If I take the square root of this will now become L naught into root of 1 minus v square by c square. Sorry, this should come in the numerator. I'll put a bracket here so that you don't get confused, into cos square theta. So this is the final expression for the length. So as you observe, when the value of v increases, definitely the value of value of L will start decreasing. This is the length contraction being seen. Okay, now let us move on to the next one. Now what's the first part? First part of it is what will be the length of the rod. We already addressed this part. Then what will be the new angle? How do I find the new angle? Now what we'll do is, let me go back to the earlier slide. So Lx and Ly I have. Lx equal to L naught cos theta, Ly equal to L naught sin theta. So I'll write down here Lx equal to L naught cos theta into root of 1 minus v square by c square, and Ly is equal to L naught into sin theta. Now, if I write the same rod here, this rod might be something looking like this over here. Might be looking like this over here. Let me assume, I do not know what is this now. So what I will do is I'll write the horizontal. This will be my angle alpha. Okay. So the rod may make an angle of alpha over here. So therefore, now we need to find this value of alpha. So what I will do, I will divide one by the other. When I divide one by the other, so what do I get here? So this will be Ly divided by Lx is equal to sin theta divided by cos theta into root of 1 minus v square by c square, which will now be equal to tan theta divided by root of 1 minus v square by c square. Now you see, this is your new length L here, right? So this was your Lx and this was your Ly. This was your Ly. So now if you look at this Ly by Lx, what is this now? Ly by Lx, I'll write down here. Ly by Lx is nothing but equal to tan alpha. Substitute it over here. When you substitute it over here, you get the answer as tan alpha is equal to tan theta divided by root of 1 minus v square by c square. Which means what? Now what's happening to the alpha? Is the alpha increased value or is it decreased value? We want to know that. So which you can see from here, that when this v is larger, this fraction, whatever we have inside this quantity inside the brackets, will become lower, will definitely be lesser than 1. If it is lesser than 1, then the numerator will be larger than it. So tan values will always increase with the value of alpha. So therefore, definitely you can say alpha is greater than theta, right? Now you suppose if the frame was moving with a velocity equal to c, then what could have happened? You put c here, this will become 0 here, this will be tan theta by 0 will be infinity, and then your alpha would have been pi by 2, right? If v is equal to c. If a rod was moving in this direction with a velocity equal to light, then the angle would have no more be an angle theta, but the rod would appear to be moving perpendicular like this. Okay, it will not be an inclined rod, but it will be moving perpendicular like this. Okay, so this is what is the answer we have got. Okay, now let us consider this problem. You have a slab of water which is moving with a velocity v, and there is a photon which is also moving inside it like this. So as we know, a photon, the velocity of photon in the air is always seen to be c. But if it is in water, what will be the velocity? Velocity would be equal to c by n. This velocity will now be equal to ux dash. Why ux dash? Because the frame is moving. This is the frame. Frame is moving with a velocity v. So therefore, it's a x prime coordinate, and this is your y primed coordinate, right? And in this frame, there's one more object which is moving. Okay, and where is the stationary object? Stationary object is stationary here, which is saying outside this frame here. I am the person who is standing outside and is watching this one here. So therefore, this is your ux dash, and v is equal to v over here, right? So therefore, now we'll write down the Lorentz equations, which tells you ux is equal to ux dash plus v divided by 1 plus ux dash into v divided by c square. This is the equation we are going to use. Let us substitute all the values now. I get this as c by n plus v divided by 1 plus c by n into v divided by c square. This square and this c goes away. So I can now write this as c by n plus v divided by 1 plus v by nc. Okay, this is the formula that we need to use to calculate the value of ux. If the value of all the other parameters are given, then definitely you will be able to calculate what is the value of ux, right? So now I have this. Let me assume, since it is water, I have the refractive index of water n is equal to 4 by 3, which is 1.33. Let me assume that this slab is moving with a speed of v is equal to, let us say, it is 0.5 c. Okay, and this is equal to c by 2. Okay, let us move like this over here. Let me substitute all the values and get the answer. So this should now be equal to c divided by 4 by 3 plus, what is v here? C by 2 divided by 1 plus, what is this? V by nc. What is v here? V is half, right? So half c divided by, what is n here? N is 4 by 3. This c is already there here. This c and this c goes away. So what do we get here? We can now write this as 3c by 4 plus c by 2 divided by, here what will I get? I get 1 plus, here it is half divided by 4 by 3. When it goes upwards, it becomes 3 by 4 here. 3 by 4 here. So which I can now write this. What is this now? This is 0.75c plus 0.5c, which will be 1.25c. 1.25c divided by, what will this be? This will be 1 plus, this half into 3 by 4 is 1 by 8. 1 by 8, right? 3 by 8. 3 by 8. Let us take ux is equal to, let me write down the equation once again. 1.25c divided by what do we have? 1 plus 3 by 8. 1 plus 3 divided by 8. So this is equal to 0.9c, 0.91c. What was the velocity of the photon inside the slab? From the, what you call, moving frame, this is only 0.5c for a moving observer. For us, it is 0.9c, right? Ux equal to 0.9c. So with this, we finish our second problem. Let us move on to the third problem. Okay. Third problem, a sphere of radius r moves with a speed of 0.7c along the x-axis. A sphere will always have the same radius. So therefore, it's moving on the x-axis. Calculate the fractional uncertainty of the volume of the sphere as seen from a stationary observer. Fractional uncertainty has been asked. Okay, the velocity of the sphere is given over here. Now, how do we solve this? Okay, let me share my screen once again. So you have the sphere, radius is like this. Now what is he asking? Fractional uncertainty of the volume of the sphere as seen from a stationary observer. So you are the stationary observer here. So you are standing here. What will happen? Anything along the x-axis appears to be contracted. Anything away from the x-axis will never get contracted, right? So therefore, what will happen? Only this diameter will now try to get contracted. So what we do is, now let us consider what is the volume of the sphere. The volume of the sphere is equal to 4 by 3 pi r cube is the volume of the sphere. Now, if it becomes something like a spheroid, then what will be the volume of it? This will become 4 by 3 pi r square multiplied by r dash, right? So as a result of it, we need to relate this r dash in terms of r. Simple. Okay, r, this is equal to saying I have a rod which is horizontal like this, of length r, and since it is moving with the velocity v, it becomes shortened, okay, by a value equal to r dash. I need to find this value. Very simple. So what do we know now? Your r dash, as seen from the stationary observer, should now be equal to r into root of 1 minus v square by c square. Simple. Now substitute all the values. It should be r into root of 1 minus, what is v here? V is 0.7. It will be 0.49. 7 square is 49, right? And this one, c square divided by c square. C square goes away. So this should be r into 1. Let us take only the root of this one. 0.51. The square root of this comes out to be 0.714. I get the answer as 0.71. Okay, so I got the answer 0.71 over here. Now what is it I need? I got r dash. Your v dash will now be equal to 4 by 3 pi r square into 0.71 into r, which will now be equal to how much? 4 by 3 pi r cube into 0.71. This is what I got. Now what is this? Now v dash, new volume. This is old volume. Now what is happening to new volume? New volume is shrunk. Old volume is larger. Now what is that I need? I need a fractional uncertainty. How do I find the fractional uncertainty? Let me write it on here. Delta v divided by vi is what I need. What is delta v now? The v 4 by 3 pi r cube minus 4 by 3 pi r cube into 0.71. 4 by 3 pi r cube into 1 minus 0.71. Right? I subtracted this from this one here. Divided by, what's the original value? 4 by 3 pi r cube. This and this goes away. So you got 1 minus 0.71, which should be around 0.29, right? Okay, next problem. So the problem states the distance of a star from Earth is 4.25 light years as measured from the Earth. So what is this given here? This tells you the distance of a star from the Earth is 4.25 light years as measured from the Earth. Okay, what is this 4.25 light years here? This is your distance. So which should be your proper length? Proper length. A spaceship travels from Earth to the star in 4.25 years. What is this now? This is your proper time. Proper time. With respect to a clock on the spaceship, what is the speed of the spaceship? Appear to be very simple, right? You can just say, okay, I'm going to divide L0 by T0, okay, and I can get the answer. You are wrong. The reason is because, see here, this L0 is measured on the Earth. Okay, L0 is measured on the Earth over here. This is your L0. You are measuring this value from the Earth. And what is this time 0? T0 is measured from here. Usually, you need to measure both L0 and T0 from one location. But unfortunately, here what you do is you measure L0 from the Earth and T0 you measure from the spaceship. Okay. Now, what is the speed of spaceship? So, how do we do? Problem appears to be very simple. Okay, but you need to think a bit and then start solving with this. Now, let me do with this one here. So, therefore, now what is the speed? Speed is unknown. Let me write the speed V over here. So, therefore, L0, see, there are two perspectives of looking at it. Either you solve it from the stationary frame or solve it from the moving frame. You can do it by either way. I prefer to go with the stationary frame. So, therefore, L0 I have got. I just want to find what is the time taken by the spaceship, okay, to reach the star, and this is T over here. Now, how do I get this value of T? T is nothing but an apparent time, okay, so which I can relate this as T is equal to T0 root of 1 minus V square by C square is what I have, right? And this is the speed that we need to define. Okay, so what I do is, this is your, I'm going to substitute these values over here. So L0, so I'll write V is equal to, what is L0? 4.25 light years. 4.25 light years, which means what? The distance traveled by the light in 1 year. I'll write this as C into 1 year. 1 year, right? Light into 1 year divided by time. What is the time here? Time is 4.25 years. I'll write this as 4.25 years divided by root of 1 minus V square by C square. I'll write like this over here. Okay. So therefore, this years and years goes over here. So 4.25 goes over here. So I have this as equal to C into root of 1 minus V square by C square. This is what I got over here. Okay. So everything else goes away. So not only square this, when I square, what do I get? I get I'll write here v square is equal to c square into 1 minus v square by c square, right? Very simple. So I'll pull this one downwards. I'll write v square by c square is equal to 1 minus v square by c square, or I'll take this one that side, which will now turn v square by c square plus v square by c square is equal to 1, which means it will be 2v square by c square equal to 1. What do I need? I need to get the value of v. So v square should be equal to c square by 2. V should be equal to c by root. That's it. Things appear to be very simple when you start solving it. Only thing is, in all these problems related to time dilation, length contraction, so on, you just need to know where to apply which one. Okay. So you can also solve this problem using time dilation, which I'm not doing it. Try it yourselves, and if possible, try to put on the solution. Okay. And if you are not getting it, do ask me. I'll definitely try to solve it for you in the next video. Okay. Now let me move on to the next one. Okay, so this problem is about two spaceships, each of same length moving the same direction with speeds 4c by 5 and 3c by 5. What is the time taken by A to overtake B? Okay, let me share my screen. If I just read like this, you will not be able to get it across. Right. Let me remove my video so it is clear for you. So this is the problem over here. There are two spaceships, A and B. See, I hope you would have done such kinds of problems in mechanics. In mechanics, what you used to do is you used to consider, okay, the total distance traveled is, it has to cover this length, it has to cover this length, it has to cover this length fully, and it has to cross this also. Okay, so therefore it has to cover this also. So finally you used to say 2L divided by time t is nothing but your V. Okay, so this you would have done it in several train problems, wherein you have one train, the other train, both the trains are moving parallelly in the same track, and they try to overcome it, right? The same way it is also here, but you need to use your transformation equations. You will not use the same old transformation, same old Galilean transformations. Okay, now let us start with this. Okay, if I consider the speed of A as viewed by B, See, if it was a Galilean transformation, I can directly say that the speed of A is just c by v with c by 5 as compared to B. Okay, but since it's a Lorentzian transformation, the speeds are very high, so you cannot consider that way. But instead, you have to use your relativistic velocity addition. So how do you do? You use the formula ux dash is equal to ux minus v divided by 1 minus uxv divided by c square. This is the formula that we are going to use. Now, what is ux over here? Ux is nothing but this one. This is your ux. This is your ux. And this is your frame velocity. This is your frame velocity. What is this now? This is your v over here, right? So therefore, this I can substitute this as 4c divided by 5 minus 3c divided by 5 divided by 1 minus ux. What is ux here? Once again, 4c by 5 into 3c divided by 5 all divided by c square. So this should now be equal to c by 5 divided by, now this c and this c goes away, so this c square goes away here. So you have 1 minus 4 into 3 is 12, 12 divided by 25, which should be equal to c by 5 divided by 13 by 25. 13 by 25, which I can once again write this as c by 5 into 25 by 13. 5 ones are, 5 5s are. So finally, you get the answer here as 5c divided by 13. What is this now? This is your ux dash. What is ux dash? Ux dash is nothing but the velocity of A as seen from the moving reference frame B over here. Okay, that's what we have got. Okay, so far what we have done, we have just calculated ux dash, which is nothing but speed of A as seen from B. This is what we have seen. What is the length covered by A as seen from B? We have to look at this also. So which will now be equal to length of A, length of the actual A plus length of B. So it should be sum of these two. Now length of B is nothing but your original length. Okay, it is nothing but your the length of the spaceship in the rest frame, which is L0. But length of A is not so. Okay, when this starts moving with this, it will observe that this length of A would be shorter to this B. So which should now be equal to L0 into the root of 1 minus V square by C square. Now let us substitute. What is V here? According to what is the speed of the A with respect to B? This is nothing but, we have seen this, this should be equal to how much? We have seen that 5c by 13, right? This was seen to be 5c by 13. 5c by 13. So therefore, now I will substitute this over here. I'll write L naught into 1 minus 5c. What is 5c? 5c is nothing but 25c square divided by 169 divided by c square plus L0. When I do this, what do I get? I take L0 common outside. This is c square and this c square goes away. And this 169 here, right? So which should be square root of 1 minus 25 by 169 plus 1 over here. I have taken L0 outside. Okay, L0 outside. I get this value here. I have no space. I'll do one thing. I'll just take this calculation and write it over here. Okay, so therefore now I have the total length traveled by A according to B is nothing but L0 into, if I take the LCM, what do I get? I get L0 into square root of 169 minus 25 divided by 169 plus 1. 169 minus 125 is equal to how much? 144. So I get this as L0 into square root of 144 by 169 plus 1, right? So 144, root of 144 by 169 should be L naught into 12 by 13 plus 1, which should now be equal to L naught into 12 plus 13 is 25. 25 by 13. I get this answer. Now what is that I need? I need time. So how do I calculate time? Okay, once again I will write it over here. So I will write time taken is equal to total distance traveled. What is the total distance traveled? L naught into 25 divided by 13 divided by total time, total velocity. Okay, yeah, which formula am I using? I am using S by T equal to V, or T is equal to S by V. S divided by V. What is V here? V, we have already found out, this should be 5c by 13. 5c by 13. 13 and 13 goes away. So what do I get over here? I get this as 5 1s are, 5 5s are. I get the answer as 5L0 divided by C seconds. Okay, so thus this is the time taken by A to overtake B from the, as seen from the reference frame of B over here. I have not looked at the stationary frame of reference. I had just been looking only at the moving frame of reference, and that's how I got this expression. Okay, I hope by now you would have understood how to solve such kinds of problems. So with this we come to an end to these kinds of problems, and in the next chapter we'll be looking at the other part, something like what do you mean by Minkowski's diagrams or Minkowski's plots, okay, and time space intervals, and after that application of this Minkowski's plots with respect to the time dilation, length contraction, and then you have the simultaneity, and after that finally we'll end up with a concluding note on the muon decay, okay, or how do you estimate the lifetime of a muon decay. Do like, share and subscribe to my channel for most of the updates. Shortly after this, I think we'll be starting with the rest of them also. So probably I'll be starting with something called as one topic per day. So be in touch. I'll let you know. So what is that we're going to do. Thank you everyone for being until the end. Thank you.